All right, guys, hello and welcome to another physics video lecture. Today we are going to be talking about magnets and electricity. All right? Okay, let's jump into it. All right, magnets. All magnets have certain properties, whether they are your typical two-sided magnets or whether they are a circular rounded magnet, and that is that all magnets have two poles. Okay, they have what's called a north pole and a south pole. All right, on a bar magnet like this, they're labeled. Okay, the red side is always the north pole, and the silver or sometimes blue side is the south pole. All right, in a circular magnet, one side is the north pole and the other side is the south pole. And what we need to know about these two poles is that if the two poles are the same, they push each other away, and if the two poles are opposite, they attract each other. So much like electricity, where we talked about positive and negative charges, if the charges are the same, they repel. Same thing with magnetism. If the poles are the same, they repel, and if they are opposite, they pull each other together. Okay? The area around a magnet is known as the magnetic field, and this is that force. So if you've ever taken two magnets and felt them pull each other together or push each other away, right, if you have the two same sides together, that's that magnetic force that you're feeling. Okay? It's called a magnetic field. Now, why do things have magnetic fields? Well, let's get to that. Oh, let's do a little quick example problem. All right. What do you think is going to happen when to these two magnets? Look at the way the poles are set up. Are they going to repel each other, or are they going to attract each other? All right. Well, looking at it, the north side of this magnet is next to the south side of that magnet. Those sides are opposite poles, which means that they are going to attract each other. Okay? All right. So that's pretty straightforward. Let's move on to what makes something magnetic. All right? And in order to figure out why something is a magnet and why something else isn't, we need to go back to where we always start. Same thing we did with heat, same thing we did with electricity, is you have to go down to the atoms of the material. Okay, what's going on with the atoms? Right? In this case, we are going to look at electrons. All right. So same thing with electricity. When we talked about electricity, electricity is just the electrons jumping from one atom to another atom, okay, and moving along. That's what electricity is. But those electrons not only jump, but they also spin, okay? So magnetism happens because the electrons inside of an atom are spinning, all right? They're spinning around. Think of a basketball spinning on your finger. Think of the world spinning around on its axis. Electrons are spinning. And the thing is that in magnetic materials, okay, those spins are going in the same direction, okay? In non-magnetic materials, those spins are random. So what does that look like? Well, imagine you take something that's not magnetic, like, this sticker right here, okay? This sticker is not magnetic. If I put it against the board, it does not stick because it's not magnetized. And the reason is that inside that sticker, the atoms inside that sticker, they're spinning all in different directions. Some atoms are spinning this way, some atoms are spinning this way, okay? They're all going in different directions, which means that they're not magnetized. In a magnetic material, such as this one right here, okay, all of those spins are going in the same direction, okay? What we say is that all of their domains line up. So you'll see this word when you're taking your quiz, all right? So here is a non-magnetic material, okay? Here, you see that some of these domains are going in the same direction. Okay, not all of them, though. Some of them are going up, some of them are going down. This is a non-magnetized material. This is what a magnetized material looks like, okay? All of the atoms inside of a magnet spin in the same direction. In this case, they're all spinning up, which is why the magnet sticks to the board. Okay, and it's why the board sticks to the magnet, is that their electrons are all spinning in the same direction, or as we say, their domains align. All right? So that would be a good thing to write down while you're taking notes, okay? Oh, I should have said this at the beginning. These PowerPoints are going to be online. I'm going to post them with the lecture, and if you want to, I think it's smart while you're watching the video to write down some notes and to go through the PowerPoint. Okay? All right. So again, if there are randomly arranged domains, meaning those electrons are spinning, we call the spins a domain. If they're spinning in random directions, it's not a magnet. If they're spinning in the same direction, it is a magnet. Okay? And again, when I use the word magnetic domains, all we're talking about, that just means which way it's spinning. A domain is which way it spins. All right, so as you probably guessed, it's pretty easy to see what objects are magnets and which ones aren't. You may be saying metals. Yes, metals are magnets, but despite what the X-Men and Magneto have you to believe, not all metals are magnets. Okay? The three most magnetic metals that exist are, pause the video if you want to guess, or, boom, iron, cobalt, and nickel. Iron is the one that we see the most. Anything that has iron in it can be magnetized or can stick to another magnet. Cobalt and nickel are the other two. And we have a word for this, okay? We call these ferrous and non-ferrous metals. If you remember back to chemistry, you may remember that the chemical symbol for iron is Fe. So we call things that contain iron ferrous. I think it comes from Latin, Greek. I'm gonna go with Latin, that's my guess. So iron, iron alloys, steel that contains iron, as well as cobalt and nickel, which don't contain iron but are also metals. Those are all magnetized. Things like aluminum, brass, copper, titanium, stainless steel, all of these things do not contain iron, nickel, or cobalt, and that means that they are not magnets. They cannot be magnetized, which is interesting. Okay? Another interesting fact, which you may not know, is that you are currently standing on a very large magnet. That very large magnet you are standing on is called Earth. All right? Our planet is a magnet. And the reason that Earth is a magnet is because the center of our Earth is full of molten lava. Okay? And a large portion of that lava contains iron. All right? Which is really cool. All right? So what happens is as that core and the bottom and the middle of the planet is spinning around, okay, as we rotate, all right, it creates a magnetic field around the entire planet, which is really useful. It helps wards off cosmic radiation. It's the reason why you see that aurora borealis, which is really cool. But it also means that our planet actually has two poles, okay? So we have two different north and south poles. All right. We have what is called a geographic North Pole, and we have a magnetic North Pole. All right, the geographic North Pole of the planet is the North Pole. That's where Santa Claus lives. All right, and it is just the axis. So when we look at the planet spinning, the geographic North Pole and South Pole, okay, are the axis on which the planet spins. The magnetic North Pole is just a hair off from the geographic North Pole, and it is the direction that compasses point, right? So when you see a compass pointing north, all right, it's generally pointing north, but it's actually pointing to magnetic north, not Santa Claus north, is how I think of the difference between the two, which is pretty cool. All right, so we are now gonna step on, so now we know what types of materials are magnetic, we know what causes magnetism, it's just the electron spinning. If an atom has electrons spinning in the same direction, its domains align, it's magnetic. Those things are iron, nickel, and cobalt. Okay, but now we're going to talk about how we can use electricity to create magnetism. All right, so how does this work? Well, back in the year 1820, a guy named H.C. Oersted, okay, discovered something that completely changed the world. All right, he found out that if you run an electrical current through a wire, it creates a magnetic field around the wire. And this is why we are able to use any kind of electronic device that we have, this electromagnetism, all right? So, simply put, electricity can be used to create a magnet. Wherever there is electrical current, there is a magnetic field going around that current, okay? So that means that we actually have two different types of magnets, okay? The first of which is called an electromagnet, and that's what Mr. Oersted here found out, okay? An electromagnet is a magnet that uses electricity to create a magnetic field, okay? The other type of magnet is what is called a permanent magnet, okay? These are permanent magnets, pieces of metal that contain iron, nickel, or cobalt. They are permanent magnets, they stick, okay? The biggest difference between the two is that permanent magnets are always on. If it's a permanent magnet, it sticks. I can't snap my fingers or flip a switch and make this not magnetized anymore, okay? But electromagnets are super powerful, and you can turn them on and off. All you have to do is just disconnect the electricity, and voila, there's no more magnetism. Okay. We are going to make an electromagnet in just a second. I'll show you how to do it at home. Where you may have seen huge electromagnets before, we use them a lot to move metal, especially in industrial sites or at like where they crush cars, right? You have this huge piece of metal. Okay, and when you turn it on, all this metal flies up onto it, which is really cool. Another way that we use electromagnets is in speakers, which is really interesting. The way that a speaker works is that it has a permanent magnet, and then it has a coil of cable around it. When you run an electrical signal through this coil, right, okay, it becomes a magnet. This is a magnet, this is a magnet. They push away from each other, causing the speaker to move forward, which sends the vibrations forward, which is really cool. So all speakers have electromagnets inside of them. Now, how can we make an electromagnet? It's actually a lot simpler than you may think, okay? So here we have one piece of wire, okay? And that wire has a current running around it. Actually, let me jump forward to show you guys something. You need to understand this right-hand rule. What the right-hand rule says is that the direction of the magnetic field wraps around a coil in the same way every time. All right, I'm getting a little flustered. So what does that mean? Let's say this pencil is my piece of wire. All right. What you do to figure out what direction the magnetic field goes is you take your right hand, hence why it's called the right hand rule, okay? Your thumb points in the direction that the electricity is going. So if the electricity is going this direction, okay, if it's going from the eraser to the tip, I put my thumb in that direction, and your fingers go in the direction of the magnetic field, right? So if you look right here, the thumb points in the direction of the current, and the fingers point in the direction of the magnetic field. So in this case, the magnetic field is going counterclockwise around that piece of wire. Okay. So in these cases, if the cable is going up, I put my thumb up, which means that the current is going around this way. Okay. If it's going this direction, I do the same thing. Boom, which means that the current is going around in this direction. And that last one, I'm not really sure why I have that there. That's just a positive. But anyways, okay, jump back. Okay, so here's my wire, all right? In this case, my current is going this way. You can see the arrows, okay? They're going in this direction. I know it's kind of hard to see directions on flat surfaces. The current is going towards me, okay, which means the magnetic field is going in this direction. That's just one magnetic field. But if we wrap this coil up, if we wrap it into a coil, we take the cable, we take the wire, we turn it into a coil. Now look at what happens. All of those magnetic fields on each wrapping line up, and they create more and more magnetic fields. And if you take something like a piece of iron, like a nail, and stick it in the middle, that increases the magnetic field even more. So I have one of them right here. I don't know if you guys can see this, but all I did was I took a nail, okay, and I took some copper wire and I wrapped it around the nail a whole bunch of times, okay? All of the wrappings are really neat and they're really tight. That's really important because you want them to all be right next to each other, okay? If it's sloppy or if they overlap or they're not all going exactly in the same direction, it means that your electromagnet's not going to be as strong. Now, to turn this nail into a magnet, all I need is a source of voltage. In this case, a battery. All I have to do is make this a circuit. So I connect one end to the positive end, one end to the negative end. I hold it there for a second. And I take the nails right here, and as you can see, boom, boom. Oh, dropped a few. There we go. That is an electromagnet. Okay, now the cool thing about this is if I turn the magnet off, if I disconnect the circuit, okay, which I'm trying to let go, all the nails fall because there's no more electricity going through it. No electricity, no magnetism. So there's a fun little project. If you have nails and copper wire and a battery in your house, you can make your own electromagnet, which is pretty cool, right? Okay, ways that you can make this magnet stronger. Number one, think of the thing that you have in the middle. We had a small nail. If you had a really big nail or a huge chunk of iron, you would have a much stronger magnet. Number two, the wire itself. If you have thicker wire, you would have a stronger magnet. Similarly, if you have more wrappings, right, the more coils you have, the stronger the magnet's going to be. And last but not least, the battery itself. If I used a 9-volt battery instead of a 1.5-volt battery, I would have a much stronger magnet. So those are all things to consider. All right, we talked about the right-hand rule. We went over this. I linked some videos. If you want to see about how electromagnets work in the real world, go ahead and watch any and all of these videos. Okay, give you something to do. Now, this brings us to our second part about this. If we can use electricity to make a magnet, the opposite of that is also true. We can use magnets to create electricity. In fact, like 90% of the electricity in your house right now comes from a magnet somewhere. So sit back and we'll see how this works. Okay, so 150 some odd years ago, two gentlemen, Joseph Henry and Michael Faraday, who are brains of the ages, realized that if you took a magnet and moved it inside a coil of wire, you could create an electrical current. I can show you this. So here is what they figured out, okay? Here I have a whole bunch of really, really nice wrapped coil, okay? This is called an ammeter, which if you remember, ammeters measure amps, and amps are how we measure current. So I'm gonna hold this here, okay? Now watch what happens. As you can see right now, I'm just holding this, you can see the ammeter reads 0. Okay, there's 0 amps there. But, it's gonna take me a second to figure out how to hold this. If I take a magnet, and if I move it inside the coil, look at the ammeter. Whoosh. Whoosh. See that? If I flip it around, it goes the other way, move it forward, whoosh, there's current. Whoosh, there's current, okay? That may not seem like a big deal, but by moving this magnet back and forth, I am creating current, meaning I am moving electrons, meaning I'm creating electricity. There is electricity in this circuit now because I'm moving this back and forth, okay? Notice that if I move it, if I move the north end to the right, I get what's called a positive current. If I move it to the left, whoosh, I get what's called a negative current. All that means is if I'm moving it this direction, the electrons are moving in the